Automated telescopes powered by AI, like the Vera Rubin Observatory, will detect over 1 million new objects by 2035. But here's a problem: we cannot characterize them fast enough. Traditional methods for determining an asteroid's orbit require months of follow-up observations. Reconstructing the shape takes years of data collection across dozens of viewing angles. Most of the time, when it comes to planetary defense, we need fast estimates before we actually need to precisely measure them. If I were to look to new solutions, I'd go with AI systems. I'm Li Fuzhang from Wellington College International Shanghai, and this is a project video introducing ASTRAIA, a multimodal deep learning framework for rapid asteroid orbital and morphological prediction. ASTRAIA stands for the Asteroid Trajectory Reconstruction and Analysis using Integrated AI. It has a two-phase cascading architecture. Phase 1 performs orbital determination, and Phase 2 takes those orbital predictions and generates a 3D model of the asteroid. The key insight is that the orbital dynamics and asteroid properties are physically coupled and constrained. For training, I merged data from the Laowa Observatory and NASA Jet Propulsion Lab databases, creating a dataset of over 800,000 asteroids, each with 2 observations. For 3D shapes, I used approximately 5,000 models of the DAMIT database and conditioned with the orbital elements from the last phase. Before we introduce the model, we have to understand what the 5 Keplerian orbital elements are. They're the standard parameters that astronomers use to fully specify any orbit around the Sun. There are 5 different separate parameters that has different properties. Traditional statistical methods struggle with sparse observational data. It's precisely where the modern deep learning excels. Neural networks can discover complex nonlinear relationships that classical regression cannot capture. My approach will leverage its power through 3 components. First, feature engineering. Raw inputs are just 6 numbers. The sky coordinates, which includes right ascension and declination, like x and y, for 2 sets. Timestamps and brightness. I expand these into 30 physics-derived features, and that each feature encodes the domain knowledge about orbital mechanics, giving the network structure representations to learn from. Feature engineering remains critical even in deep learning. Second, the attention mechanism. I implemented a head multi-head attention. Why attention? Because the orbital prediction requires modeling long-range dependencies across the entire feature space. Different heads specialize in different relationship types. Some captures motion patterns, others geometric relationships, and others temporal correlations. The network learns which features interact matter most for each prediction. Third, specialized output heads. Each orbital element gets its own prediction head with tailored architecture. The key innovation is handling angular outputs. Angles wrap around each other, so 359 degrees and 1 degree are actually close, but in terms of the loss, they are far, far away. I use a unit vector representation, predicting sine and cosine components separately, then recovering the angle, which eliminates the discontinuity problems that will otherwise destabilize the training. Now for phase 2, which is the conditional generation of the 3D models. I adapted Trellis, which is a VAE-based structured latent diffusion model for asteroid shapes. The key architecture, the choice I chose, is a sparse voxel representation, efficient for irregular geometry since we don't need to waste capacity on the empty space inside. The 5 Keplerian orbital elements from phase 1 inject as conditioning vectors through cross-attention layers. They are used as the input, and the guided generation towards physically consistent shapes, which the 3D models will be the output. Training strategy matters here. With only 5,000 shape models I used in my dataset, I used transfer learning. I froze the pre-trained VAE decoder and only fine-tuned the sparse structure flow component. This prevents the overfitting while adapting to the asteroid domain. Outputs includes meshes, 3D Gaussians, and radiance field, generated all under 3 seconds. Now for the results, phase 1 orbit size prediction achieved a 5.51 mean absolute percentage error. Orbital tilt, which is the inclination, achieved only 2.4 degrees of error out of 180 degrees. R squared of 0.741 on a main asteroid population confirms a strong predictive correlation. The model learned the orbital mechanics, not just memorizing the training data. For phase 2, reconstructing MSE of 0.057 beat the 0.1 target. Against baselines like Shape E, LGM, ASTRAIA achieved lower frechet distances and higher clip alignment, all indicating that the geometric accuracy is much higher than the previous models. The total pipeline, under 10 seconds for complete characterization, is also the fastest of its kind. ASTRAIA is an AI engineering project that demonstrates that physics-informed neural network architectures can solve problems previously considered physically impossible. The combination of attention mechanisms, structured feature engineering, and conditional generation achieves 3 orders of magnitude speedup over traditional methods. The framework validates that deep learning can extend AI's reach into scientific domains while still relying on classical computation. Thank you.